All right.
Bob clap. Yeah, Bob clap. All right. We're going to agree on 2 dimensions first, right? So, be sure you know what I'm talking about. Measure the diameter and the area of the lifting cylinder. Lifting cylinder is the big guy, right? Oh, yeah. Symbol for cylinder is that simple, right? So it's 0.945. The area equals what?
0.75.
0.701 is called, right? Just because it makes a big difference in this case because we were generating such high pressures. Number 2 is, we said, 0.3 inch. This is the pumping cylinder, right? The diameter is going to be 0.43 inch. The area equals what?
0.145.
I'm sorry?
0.145.
145. I don't have units on this yet, do I? What are these?
Inches squared.
Inches squared. Number 3 is to determine the stroke of the lifting cylinder. We all agreed it's 4.375 inches, right? It's just a linear dimension, one dimension, right? Stroke of the pump cylinder is what?
0.75.
So 3/4 of an inch. And that's just this limitation, right? This physical limitation right there. This guy lifted from all the way up to all the way down, or from all the way down to all the way up, is just 3/4 of an inch stroke, right? Number 5.
The area times the stroke.
So it's to determine the volume of oil needed to fully raise the cylinder. If we look at this cylinder, we draw it. Here's the casing, right? I'm sorry, no, we'll just look at the cylinder itself. So it's really just the stroke. Number 5 is simple enough. I'm already getting advanced. The stroke times the area is going to equal the volume, right? So it's just what?
3.06.
So it's 0.945 times, or squared, times 0.7854 times point.
Don't you do the area then?
You
got the diameter.
Or to get
The area is 0.701.
Okay, let's take that. We already have it up here, right? 0.701 inches squared times the stroke is what?
4.375.
4.375 inches is the first. I add those together and I come up with a volume, inches to the third, and it is
3.0767.
3 what?
3.067.
3.006.
067.
307, right?
Yeah.
3.07 inches cubed. Everybody agree with that so far? All right, number 6, calculate the approximate volume of the reservoir. This is similar to what you do for trying to get the effective area of a cylinder, the rod side of a cylinder. There's only this donut shape that's usable. We don't get the full cylinder, we just get this donut shape. So it's got this center area here that's kind of blocked out. The big mistake everybody makes is they'll subtract these diameters from each other and figure out the area. Can't do that, right? You guys subtract the areas. You can't subtract the diameters. I see some people kind of looking
Oh,
perplexed.
yeah, I thought you were looking at the plunger and all, is there a little raise in it? You know, on the plunger,
Yeah,
has a little nipple on it?
yeah.
That's what I thought you were talking about.
No.
I understand what you're saying.
I'm just talking about the fact that the reservoir is this area all in here, right?
Right.
It's, looking at it vertically, it's this cylinder with this housing wrapped around it.
Right.
I don't get any of this space to store oil, I only get this space out here, which when I turn it right side up, looking at it from the bottom or top, I'm looking at the donut shape. So in order to do that, I subtract this area, area 1, from area 2, right? And area 2 is the whole thing. Okay? And what do we get?
3.468.
4.5. just so everybody gets the same math, let's take the two areas. So area 1 is what? Oh, I'm sorry, area 2 is what?
3.07, I just figured it out.
3.07. No, that is the volume, that's not the area.
Oh, I'm sorry, yeah, go back,
It's .7,
yeah.
.701.
That's the inside diameter, right?
And
Yeah, different. It's the outside diameter,
It's
right?
Outside.
Point-
Yeah.
1.7, then you gotta square it, times the constant, 0.7854, yada, yada, yada. And it's 7.817 is the area of the big guy, to the fill hole.
So we agreed that the two dimensions are what? The inside diameter of the housing is 1.75, right?
Yeah,
Okay, so that's gonna be squared, we take the area of that guy. What do we get for that area? Just bear with me.
10.52,
Pardon?
10.52.
No, it's.
No,
it's
it's
2.41.
Oh,
Thank you.
2.41.
Inches squared.
Yep, 2.41.
That's the housing
Yeah, .99 is
And then
the.
ID, all right?
Yes.
And then we take this minus the cylinder OD, right?
1.23.
And its dimension was 1.125. We take the area of that 1.125, that outside dimension of this guy right here, right? This cylinder right here, the OD of this guy, we're taking the area created by this, what this displaces, and we get what?
.99.
0.9,
1.99 inches squared, right?
yes.
And we get what?
So we have to,
We subtract the two.
yes.
And what is it? 2.41 minus 1.8 is 1.42 inches squared. Now we actually want to figure out the volume of this reservoir. Well, we go up to the bottom of this weep hole, which we all agreed was what dimension?
3.25.
3.25 times 3.25 weep hole
Go there.
height. And we get what?
4.61
4.61
inches cubed.
inches cubed, thank you. It's a volume, right? Volume is always a cubic function. We had area, which is always squared, times another dimension, which is going to make it cubic, right?
We figured out volume and volume and subtracted them. And we got close, but we got, 4.5, basically 4.6.
Yeah, you're doing the same method. So this, method 1 is find the area of these two guys. Method 2 is find the volume of this cylinder with its outside dimension and the volume of this whole thing and subtract them, and you'll get the same answer. You're roughly, you're in the same, you're actually real close, right?
Yeah.
Plus or minus 5%. So yeah, it's the same method, or say it's a different method, you get the same answer. All right? Everybody on board so far? 7 is what? Examine closely and state briefly how a cylinder over travel is controlled. This one's a little tricky, but I like hearing everybody's ideas. What do you think is keeping this guy from, as you're pumping it, over extending?
Loss of pressure.
It is. What creates a loss of pressure though?
That little
It's not mechanical. I kind of stated that out there.
When the O-ring falls in that divot, you got a little play, and it would probably let pressure through.
And that's it. That's it. That's exactly. So it's going to hit, not a divot though. A better name for what it hits is
It's
this.
machine divot, I don't.
What's that called?
It's a notch,
Or
a
it's,
groove, or bypass.
it's a groove that's connected. But actually, the real
Is it
leak
pumping
on it.
back into the reservoir? You over pump?
Yeah. What happens to the reservoir is this guy, right? As it overflows, it goes right back into the reservoir right here, right? So anything that comes out of the leak side of this guy is going to go right back to where it should be.
Just a hole in the top?
What's that? That would wear out the seal, wouldn't it?
Oh, yeah.
If you had a hole there that would deform and the seal went out every time, they caught that lip and they come back down, it actually deformed the seal. The reason I mention this is the same design that's been around for decades, I mean like 50, 60 years. And they haven't changed because it's a really good design. They can't make it cheaper and more efficient than it actually is right now. So there's two things that are going on. This top of this cylinder is chamfered, is the word. There's a chamfer at the top of it, right? So look at it this way. This is cylindrical here. if I take the seal up and I go beyond this, all of a sudden the ID gets too big for my seal to make it anymore. Anybody ever pump one of these guys up? Pump it all the way up to the top? What happens when you get all the way to the top?
Goes up and down.
Goes up and down, exactly. What's happening is, it's going up, you still have more fluid to pump, it's pushing it up, but you step halfway through your stroke, all of a sudden it's falling back down, isn't it? You're flowing out, but there's no seal left anymore, and it falls back and gets reseated over and over again. So you get this little oomph at the top, but you don't really get anything. You can do it all day long, and it's just gonna go and back down, and back down, because it's just pushing it to where it leaks, and then settling back down. So that's 7, right?
So what's the notch?
The notch is actually where it starts to leak if you're pumping slowly, but if you're going fast, it's hitting that chamfer. But if you're going slow, it's actually gonna hit that chamfer and start to fall back down, or that notch in that sheet. So the leak can happen through 2 different methods. And Dean's got a good question. There's a notch in here that's grooved in here. That'll actually leak, right? So it's actually gonna always fall back down this first inch, but it's gonna do it really slowly. Because it doesn't leak very much through there. This is the real safety. It catches that chamfer, and then boy, it's saying, I can't go any further than this. This is actually not mechanically, if it goes beyond where this notch is in here, all of a sudden it's supporting it with, so this is not just a sealing here. Here's the rod coming down inside here. If I start to come out of here and I'm captured here, all of a sudden, I need at least an inch in here to create another, so it doesn't start to teeter, right? So that this rod doesn't actually start to come up and fall out and wear out this portion up here. So it's actually like, it needs to be in just a little bit to really be strong. So it wants to protect that. But you can get beyond that with lower pressures. If you're at real high pressure, maximize this guy, it's going to hit that channel and pretty much leak everything out of there before it can actually get all the way up. If you're doing a couple 100 pounds, it's going to go up to that chamfer point. All right? That's 7, right?
How are you gonna work that, loss of pressure? Or
Through-
chamfer?
Through a chamfer or a notch that provides a leak, right? That allows a designed leak. Number 8, if the load on the jack is 2 tons, which is what this guy's rated for, right? Determine the amount of pressure needed to raise the load. Not really raise it, but balance it out so it can hold it or support it. How much pressure?
5,700.
Yeah, how'd you get there though?
We did 0.945 squared, the diameter of the lifting cylinder, then times the 0.7854.
Yeah, so I've got 2 tons up here, right? Which is equal to how many pounds?
4,000.
4,000 pounds.
And then you pretty much just take that and divide it by the 7.701.
Yeah, my area.
Yeah,
So-
very good.
Pressure is equal to force divided by area, right?
Yeah.
I've got 4,000 pounds of force. I've got 0.701 inches squared of area. I take this 0.701 and divide it into my 4,000, and this is really the pressure you're creating inside this jack. And back to the design of this jack, I think we talked about this before. This is a standard ANSI nipple that's rated, stainless steel nipple that's rated for like 10,000 PSI. So they don't have to machine something that's going to be rated for these super high pressures like this guy. They can take something off the shelf, really cheap nipple to a given size, probably remachine the threads on it, but and it's rated for that high pressure. Could you do that with a copper pipe? No, right? It's got to be something really substantial. I think it's just schedule 40. So if I divide that out, I get 5,700 PSI, 5,706 or something like that.
Right.
57 pounds per.
PSI, which is pounds per square inch, right? Remember, you can look at a gauge and figure out Pascal's law. this relationship is right on the gauge, right? Force equals the, pressure equals the force over the area. It's pound PSI, pounds, which is force, right? Over area, which is square inches. PSI, pounds per square inch. That was number 8. Number 9. What force is being placed on the piston rod of a small cylinder? We mentioned it out in the lab already. If I've got 5,000 pounds, 5,706 PSI, below this now, created by this force over this area, I've created this pressure, 5,706 PSI. That's going to communicate directly to my small cylinder, right? What's this pressure in here going to be? Aaron, what's the pressure underneath this guy?
What calling on me? 800, 828.
What's the pressure in here going to be?
Same, 1.45.
I'm hearing a lot of numbers. It's 5706. I'm asking you a question that's really
Oh,
so
sure,
obvious. you're
okay,
making
fine,
it
I'm
difficult.
looking for the answer though.
Yeah, it's 5706 PSI. Same pressure. Pascal's law says any pressure within a
So
chamber
that's
is the
number 9,
same.
is the same?
No.
No. I'm still working on number 9. We're not done yet. How do I know that? If I put,
Tricking me, you know?
I'm going to refresh your memory. If I put 32 inches of mercury into this room of pressure, remember, little around atmospheric pressure we measure in inches of mercury. If I put 32 inches of mercury pressure in this room, what's the pressure up in this corner or on that door or over here? Same. How would I know that? If I sealed up this room and I tapped into it and put a gauge, I'd read the same anywhere I put a gauge, right? It would read 32 inches of mercury. Same is true for this guy. It's like we're inside this room, only we've got a hallway here, and going into this room, it's going to be the same pressure. Again, this is what hydraulics is all about. If I generate pressure within a pump, apply it to a piece of pipe, go through hoses, go out to a piece of machine, I've got 5,000 PSI here, I've got 5,000 PSI out by the machine. It's a great way of using a small little conduit to transfer this tremendous amount of energy, 5,000 PSI. All right, so now the question is, what force am I generating, or what force is required to come down on this guy to balance this out, to actually want to start to lift this guy up?
It's the ratio.
Yep, so force is equal to what? Pressure times area. We know our pressure already, right? What's our area?
0.15.
5706 times point, what is it, 145? Equals
827.27.
327 pounds of force, right? Remember, this guy is PSI. That's a squared function, but it's force divided by area, inches squared. If I divide that into this guy right here, this 0.145, that's an area too, right? These guys are left with just no area at all. Area, inches squared over inches squared, cancels them out, right? So I end up with just pounds. So number 9 is 827 pounds of force. Number 10, based on a foot-long handle, determine the force required on the handle of the jack in order to raise the 2-ton load. So I've got a teeter-totter, and we agreed here that this guy's 1 inch long. If I put a handle on here, I've got 12 inches out on this side, right? So I've got a 12-to-1 mechanical advantage.
827 for that.
Yep, so I've got 1 over here, 12 over here. I've got 800 pounds over here. I'm sorry,
4,000.
what do I have?
827.
827.
Put on the other
Oops,
side.
827. So This force times lever arm is gonna balance out with this one. So 827 times 1 equals 827 is gonna equal force divided by, times 12. I wanna get rid of times 12, I divide this by 12, right?
Yes.
Anything I do, when I do on the opposite on the other side of the equal sign. So 827 divided by 12 equals what?
Like 70 or something.
68 pounds.
68.9
68.9, what?
over 1. Oh.
Pounds.
Oh.
So, that sounds pretty realistic, doesn't it? This is the real application. This is a 2-ton jack. How many pounds of force do you think it takes on the handle, a 12-foot handle, to actually lift a 2,000-pound load? 68 pounds. 68 pounds out here on this handle is going to let me lift 4,000 pounds. That's due to the mechanical advantage and the hydraulic advantage. A hydraulic mechanical advantage all balance out to give us this tremendous amount of force. So 68.9 pounds. So, we talked about this mechanical advantage of 12 to 1. If I have, say, 2 feet over here and 6 feet over here, what's my mechanical advantage? 3 to 1, right? If I have a gear or a pulley that is, the circumference around here is 6 inches, and the circumference of the mating gear is 2 inches, what's my mechanical advantage?
3 to 1.
It's a 3 to 1. This is the way I can get this with a mechanical device in 2 different ways, with a lever or with a gear, sprocket gear, right? I can get this mechanical advantage. I'm going to be able to, if this is the turning and this is the turn, right? I'm going to generate more torque. I'm going to be able to do the same thing that this guy's doing, right? But if I spin this the opposite direction, I'm going to get more speed, right? Aaron, you get that?
I'm already on it, boss.
Okay.
I don't know why you keep calling on me though. I got it, I'm
I'm
proud.
not big on it.
No, alright,
I like it.
take it easy.
All right. So if I do it with this guy right here, what's going to happen? If I move with this guy right here, I'm going to get a lot of speed, right? This guy's going to fly up and down, especially if I had something that's like 6 feet on one side and 6 inches on the other. Boy, I could move this guy over here really fast, couldn't I? But if I put any weight on there, it's going to overcome me right away because the mechanical advantage of weight is on the other side, speed is on this side, or distance is on this side. We're going to compare that now to what we just did with this guy right here. This is like having 2 gears here, or a lever. I've got a small little cylinder, right, and I've got a bigger cylinder. If I compare the input, right, of 800 pounds, I'm putting 800 pounds on this little cylinder. What is it? 827. Let's take the lever arm out of it for a second. And I've got the big cylinder here, and I'm getting 4,000 pounds. What's my mechanical advantage?
5 to 2.
Roughly.
Oh, 5 to 1.
5 to 1, right? But what do you think happens when I go to pump this guy? What am I losing? So I'm moving this guy, how much movement? I'm only getting 1/5 the amount of movement, right? I'm getting very little movement because I've got this, and even less when you have the mechanical advantage, right? So it's 1/5 times the 12 inches, right? The 12 to 1. So really I'm getting 1/30 of them, or 12 times 5/60, 1/60 of the actual movement, because I'm actually putting a 12-inch lever arm on this guy. So but taking that into consideration, just taking into consideration the amount this piston's moving, I'm getting 5 times the amount of force when transferring pressures in this direction, but I'm doing it at the cost of having to move this guy 5 times the distance. That make sense? Just like this pulley, just like this lever. All right?
number 11, I think.
11. How many strokes of the handle will be required to fully raise the load? How'd you get that?
You took the volume of the big cylinder, and I believe we subtracted the volume of the little cylinder,
No.
divided the volume of the little cylinder.
Yep. So we knew that the big cylinder volume is how much?
307?
Pardon?
307, 3.07.
Yeah, 307.
And then full answer would be the,
Right, inches cubed.
yep. And we're gonna divide that, that's the big volume of this relationship is this big cylinder here compared to this little guy here. This volume is this guy. This volume here is how many times we're gonna actually push that little guy into this big guy. So it's just
0.7.
dividing it by 0.7, is it?
0.701, yeah.
0.1. And we
No,
got how many
no,
strokes?
The area is .7.
We have- oh, yeah.
You gotta times it by .75 for the stroke.
Yeah, so it's, this
One,
volume
two,
here
five.
equals what? 0.701 times the 0.75 stroke, right?
And then the answer
Well,
would
what
have
did you do that?
.1089.
0.109?
Wasn't it .10?
I got 89, but .109.
So this divided by 0.109 gives me about 30 strokes, right?
I got 28.09.
28 strokes, okay, equals 28 strokes. Everybody understand that?
Yep.
Are you sure? A lot of times people, everyone got that?
There is another way to do that, correct?
Yeah, that's pretty much it.
Well, what we did is we figured out the volume of the small cylinder and transferred that into the,
Transferred it by dividing it, right?
yeah. Basically, we took
Small?
0.109 inches cubed, divided it by 0.701 inches, which is the diameter of the cylinder, which is the, we came up that for every full stroke of the small cylinder, the large cylinder is going to go up 3/16 of an inch.
Wow, I'm not sure that sounds like, this is a lot easier.
It is, but
And
we
what
we
does
got the same answer.
So
Yeah,
then-
we went through more work, but yeah.
Yeah, I don't doubt that there's a different way of doing it, but it sounds like it'd be pretty difficult. So you determine for every stroke what distance you went and then divide that into the linear dimension. It is a different way. That is absolutely correct.
Well, if you draw it on the board, I can explain it to you.
I think we better finish up, and then because that is correct, but I don't want to confuse everybody right now. Because it's transferring a volume into a linear movement and dividing that linear movement into a volume. Yes,
That's not how we did it though. We took the areas, multiplied them together, and then divided by the inches of stroke. And that's how we determined that we had 28.
Okay, so, number 12, if you apply excessive force, does the jack have a relief valve?
No.
Now, simply put, that's just a question to show you that this is a simple device. What's probably going to blow on this guy? The seal, yeah. All right, so using ANSI symbols for cylinders, reservoir, check valve, needle valves, draw the jack. Who wants to take a stab at it? I want to pick up Aaron just to see him explode.
I can't. We're done to 11. I had them all, but I was a couple points off on every single one.
What do you mean?
Right.
We're
Decimal points.
Yeah, we were decimal points off.
On all this stuff?
Yeah, so I had it the whole time, that's why I'm looking here bored. I just wanted to find out the answer to assess my answer, and you kept being confused that I didn't understand.
No, I just saw
understood
you
the whole
bored, so
time.
I thought he'd engage you.
No. Damien's been tutoring me, so I've been doing pretty good.
Good. All right,
But I cannot draw it. But
I kind of started to draw it already. We have a small cylinder, right, and a big cylinder. Let's go ahead and erase this guy. Come on, somebody's got to have it. Who thinks they have it right? Damien? You have drawn it up?
I approved it.
Did I draw it? No, I have not drawn it.
Can you draw it?
We're gonna find out when this test comes.
These guys are obviously connected to each other, right? We got a line in between these two guys, we know that, right? One's pumping into the other guy, the
Is there a
small
check
guy.
valve?
There's a check valve, there is. Where do you think that check
I
valve
think
is?
it's on the small guy.
What's that?
Is it on the small one?
So is it this, so I've got a check valve.
Right.
Tell me, what's that? You think it's on the big one?
Because if there's gonna be that much
It's
pressure
got-
created,
it's
you wouldn't want that
in
in
the-
the.
Let's do this first. We know this is coming from a reservoir, right?
Yeah.
So the check valve would prevent you from pushing oil from the small piston back into the reservoir.
Yeah, so would it look like this here or the opposite direction?
The opposite direction.
Opposite direction? Like that? Everybody agree? Good. All right. We know that this guy can let oil back out of it, right, into the reservoir. So, right? Do I have two reservoirs?
Just one, just go.
This denotes one reservoir, right? Instead of having lines coming back from everything back to one reservoir, which would really make a drawing really messy, you have multiple reservoirs depicted out there, but there's only I only know one reservoir in any system I've ever looked at. You don't have two reservoirs.
But you don't put a note, like reservoir. You know, I'm just saying, you don't, main reservoir,
So you
main
never see
reservoir.
one with two reservoirs?
You don't use notes?
No, it would be, and the reason I think you'd see that is because you could empty one out, right, and run into troubles. How do you know if you're gonna overflow one or empty the other? You'd run into big problems, right?
But you can't just go
Yeah,
straight back to the
yeah.
tank.
Don't steer it to a check. valve.
No, because there's something on this guy, right?
Yeah.
What lowers this jack?
The relief,
Needle valve.
needle valve.
Needle valve. It's a needle valve, right? It's threaded, it doesn't have a relief because it has some type of spring or something that would relieve the pressure automatically. This is just human intervention that's coming in there and opening or closing something. What does a needle valve look like?
Sideways panel
Block.
with a.
Two E's.
It's kind of
One
like
with
that.
the.
Sad and smiley face, yeah, right?
Yeah.
Right?
Kind of
So
like
it's
a
got
baseball.
happy face, sad face. What else?
That's a needle valve?
Arrow going through it.
Damn, I thought it was two
Oh, the
E's.
line through it.
That's
Okay.
it, isn't it?
It's an adjustable orifice, right? This is an orifice.
That's adjustable.
And you'll see these called out sometimes as like .06, that's a 60 thousandths orifice, right? But if it doesn't have this, it's just it's a fixed orifice. What do I need to it to adjust it? That means adjustability through anything, right? You can manually adjust it, right?
Where'd you just write that?
Pardon?
Oh.
This, I created so I said that this is just an orifice. This means I can adjust that orifice. What's an orifice? A hole, right? So now I've got this line coming through this guy. I can adjust whether I want to close this off or the speed, right? So this isn't just a on off like a globe valve or a ball valve. Oh, everything would just boom, drop down, right? I can adjust how fast I want to let this guy down. What's missing from this guy?
So what happens if it was the ball valve? How would that look? I'm just curious.
Uh,
How would you draw a ball valve?
Ball
Because
valve-
it's not necessarily adjustable, but it is. Okay, it would just be all right, just
You
curious.
have a directional control, two-way actuator. Or, oh my God, it's called. So,
No, there's no actuators on this
No,
valve. It's all manual,
two-way
right?
directional, cylinder.
Yep, so now what's left, what's missing from this guy? What's wrong with this? If I raise this handle, if I put this and draw it just like this, right? How's the system gonna operate? Sure, it's gonna lift up and pull fluid just fine in this guy, right?
You know the check valve from the large.
Is it?
So that's go back.
If I lift up, I'm sorry, go ahead.
You need another check valve from the large one, so it doesn't try to go back. to the
Exactly,
small
right? So I need this, don't I?
Yeah, opposite.
Opposite direction.
So when I draw from it, it's only drawn from this guy. It can't draw from the big cylinder, right? You know what this is? This right here? This is the most basic pump that we've seen from like thousands of years ago. Anytime you have a line in it, and it's got two check valves like this, you basically have a pump. This is all the veins in your body are operating in the same method. There's no pressure, right? Your blood comes out from your heart, goes through your arteries, under pressure, right? Everyone has like 110 over 20 or 110 over 80 or whatever. That's pressure in inches of mercury, I think it is. That is transferred out to your capillaries, goes through the cells, comes back and gets into your veins. What's pumping that stuff through your veins? How does it get pumped back up to your heart?
Suction?
No suction.
Check valve.
Right, check valves, yeah, it's this. So if I got this vein sitting here, and you guys have done it, right? You've found the check valves in your veins before?
Pulse.
You push against them? Yeah, if you find a vein and you push up against it, you can only push in one direction. It'll empty out, you can empty it, and it'll stay empty. I release it, it opens up. I can't go the opposite direction. All throughout your vein, all throughout your whole body, the veins are a series of check valves that, once they fill up, it's like a peristaltic pump. If I push this out of here, where's the blood going?
That way.
Which direction?
To the left.
To the right.
To the left. It can push
To the left.
against this and push this guy out, right? So it's going this direction. I all of a sudden expand that vein now, where's it going?
Everywhere.
Nope. It's coming from this guy. This guy will feed it, right? It's just like in a peristaltic pump. If I squeeze a line, I'm going to push out in this direction. I relax that line, it's going to suck in from this direction. Just like this guy's doing.
So you said suck, so I was right, suction. Because whenever you.
It's not vacuum.
Low
It's not
pressure, low
subatmospheric.
pressure goes to,
Unless you're from
High
another
pressure
planet,
goes
nothing
to
in your
low
body is subatmospheric, right?
well,
It's a refrigerant. High pressure to low pressure.
I never said vacuum.
Okay, you're right. I guess it's lower pressure. All right. But if you open up a diaphragm pump, it's the same principle. It's going to have a diaphragm sitting in there. You're going to pressurize one side. It pushes peanut butter, gas, whatever on one side, pushes it up through a check valve. Comes back the other direction, allows it to come through a different check valve. Back and forth. So this principle of a pump is something that's pretty good to understand when you start ripping into any type of even complex pump. All right, so where are we at next? That's the ANSI 14. If this jack, this same jack, I think this is where everyone got confused. This same jack is rated for 14 ton and has a 3-foot handle. What pressure would be created?
$40,000 PSI.
Yeah, like 4,000 PSI.
40,000, you gotta add another.
You got how many PSI?
39,000.
Yeah, it's huge. It's a huge amount of PSI. It's going to be
Because the
what?
tons, remember, it's 2,000.
39,934 PSI.
It's 28,000 pounds. Divided by what?
0.7?
0.701. 8 inches squared, pounds. So I get my PSI, pounds per square inch, and I get what?
39,934 pounds per square inch.
All right?
Did you take the original 5706 for the 2-pound, for the 2-ton jack,
Yeah.
and just times it by 12? Because you already had the 2 from previous.
No.
Okay, good, I see it doesn't work, I was just asking.
Do you know why it
I
doesn't
see
work?
that now.
You're confusing units. Now, if you took it, the ratio, we went from a 2-ton to a 14-ton, right?
Right?
How many times did we just increase the capacity? of this?
7
7.
tons. So
What's this guy right here times 7?
There you go.
39,943.
Oh, I did it by 12.
There you go. That was a way of doing it. That was a simple way.
Okay, that's what I was looking for, but I did it by the wrong, I did it by the tonnage, not by the PSI.
Yep.
All right, that's what I was looking for.
All right, so now it's asking, what force on the handle would be required? Well, it's a 36-inch handle, isn't it? It's got that same 1 inch, so it's 36 to 1.
Couldn't you just take 69 pounds times 7?
Well, we got to think in our head for a minute. We got 40,000
times 0.15 or 0.145.
Yeah, we got to start figuring out the force that's on this small piston over here. Small piston is how much, what's the area on the small piston?
0.145.
0.145 times this guy right here, right?
Yeah.
Equals, how many, equals pounds, right? And how many equals how much? This is pressure times force,
So,
I'm sorry, pressure times area.
5
equals this force.
5,790.
Yep.
5,790.
5,790. What's my full answer?
I don't know what the question was.
Pounds.
Pounds.
Pounds, yeah.
That's why I hate, when you get caught up in just the numbers and the math, you kind of lose track of what you're actually figuring out. So it's 5,700, or 5790. What's our last step?
Divided by 36.
Yeah, it's a 36 to 1 in mechanical advantage, right?
Right.
Divide that by 36, and I get what?
160.28.
So, this is a floor jack, right? The one underneath the stairs over here. I think it's rated for 12 or 14 ton. I can go 160 because the average guy weighs probably about at least $180, right? He can put himself on that and raise a 28-ton semi because he's got that ability now on a 3-foot handle to generate with his 160 pounds, his full body weight, this kind of pressure. Transfer that same jack, and most of the jacks are going to use about that same size cylinder. Some will be bigger, and I can actually lift a semi truck. But look at the pressure you're creating. 40,000 psi. You wouldn't think that would be.
What's
Pretty
that,
solid walls.
what's that nipple rated for?
Yeah, I'm sure there's not a nipple in there. That's going to be a honking chunk of metal to actually be able to handle that. And the seals on that, it's not going to be one seal. It's going to be like 3 or 4 of them, right? Going down there, so that there's going to be blow by the first cylinder, second cylinder is going to catch it. So there's a series of seals that actually seal it up.
Well, do they even sell a jack that big?
And the stairs are right here.
Oh, okay.
Yep.
Floor jack.
Yep, floor jack. You're raising a
Oh, like
semi.
a NASCAR one?
Yeah.
No.
It's the rolling
Go
project.
Yeah, rolling floor jack, especially the ones that are rated for semis. They're huge.
Right.
And they're... Okay, so that's it. Questions, comments?
What's that, Madison?
What's that?
No, I want you guys to keep it. What was the extra credit?
Which jack, 214 pounds, you raise a 18-pound car and two,
Oh, I forgot about this. It's not on mine, so this is new this year.
I'll take full credit.
What's the answer?
I think more energy.
It's a trick question.
It is. Why is that?
It's the same.
Right,
But in
because it's,
addition, it only has a stroke of 4 inches, so it can't raise it 2 feet.
because the energy is gonna be the force times the distance divided by time, over time, right? It's the same for each one. Right, they even out. If I raise